Okay, Statistics, Chapter 8, Section 1, the distribution of the sample mean. What this lesson is going to be predominantly about is that if you take a sample, and if the population is already normal, you're going to take that sample and you're going to take the average of it and record that data number. Then you're going to take another sample and record its average, and another sample and record its average. And then you'll run statistical analysis on those sample means. So this lesson today will be talking about the means of samples is what our actual data values will be that we enter. It talks about the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2 and 46/100 gram and a standard deviation of 0.02 of a gram. Approximate the sampling distribution of the sample mean, obtaining 200 simple random samples of size 5 from this population. So the original data is already normal. And so if we take the means from data that's already normal, our new data will also be normally distributed. So what's happening here is they're saying that they took sample sizes of 5. In other words, they drew 5 pennies out of the population. They took the average of those weights and they recorded the value. And this was the first group of 5. And then this is the next group of 5, the average of their weights, the next group of 5, the next group of 5, and so forth. And they did this 200 times. Note that the new mean, the mean of all of these sample means happens to be 2.479. The original mean of the entire population is 2.46. That's really close. If I took a look at the original standard deviation, that would have been the 0.02 of a gram. When I took 0.02 of them, notice my standard deviation now is much smaller. The standard deviation will shrink as your sample size gets larger, and that's because the standard deviation you will now take and divide by the square root of how many is in your sample. So my new standard deviation, I take the original, which was 0.02, and divide by the square root of 5. There was 5 in this sample, and that's my new standard deviation. In the second scenario here, there was 20 in the data set, so I took the original standard deviation divided by the square root of 20, and that's where I got the new standard deviation. Again, the original population was normal, so the sample size I take doesn't matter. My data will still be normal. The means will remain the same, but the standard deviations will be shrunk by, you will divide by the square root of n and how many is in the sample. And so this is where we're talking about as n got larger, the standard deviation will get smaller. So the weight of pennies minted after 1982 are normally distributed with a mean of 2.46 grams, standard deviation of 0.02. What's the probability that in a simple random sample of 10 pennies minted after 82, we obtain a sample mean of at least 2.465 grams? So again, we're talking about the average of a sample. We're not talking about an individual penny, an average of a sample. See, I want to know the probability that the average of a sample, see, notice this is an X bar, not a plain X, that the sample average is more than 2.465. So if we know that the mean of X is normally distributed with the mean for the mean of X to be remains the same, 2.46, but the standard deviation we divide by the square root of how many is in our sample, which was 10. There's my new standard deviation. Now all I need to do is get my z-score and then take a normal CDF from that z-score, in this case to 100, because I want x is greater than or equal to. So to get my z-score, remember we take this value, our x value, minus the mean, divide by the standard deviation. So we're going to take our x score here, 2.465, minus the mean, divide by the standard deviation. That gives me my z-score. That's what this falls here, that z-score of 0.7937. So I want to know the area from that z-score and to the right, so that would be a normal CDF from that z-score to the right, which is 21.37%. So now what if my population was not normal to start with? If the population is not normal to start with, for example, if I was to roll a dice, probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6 are all equal. They're all 1/6. 1/6 is this as a decimal. So if I was to type all of these values here into L1, all the probabilities into L2, run a normal CDF on that, my mean would be the 3.5 with the standard deviation of 1.708. The graph would be a uniform Okay, it's all about the same probabilities. So instead, what if I took and rolled 4 dice? I'm going to roll 4 dice, take the average of those 4, and record my data value. Then I would take that's what this is here. If I was to take 10 dice and take the average of the dice that I just rolled and record those data values. And in the last case, if I was to take 30 dice, take the average of the dice that I just rolled and record those data values. Now I want you to take a look at these graphs. I want you to notice the graph. So the larger that n gets, the more normal my graph is looking. Remember, the original graph wasn't normal. It was, hopefully you guys are thinking about it, it was uniform. Remember, that was the uniform graph. Okay. Now if I take a look at the means, the mean on all of these falls at about 3.5. The mean is about 3.5. The mean on this one is at 3.5. I do hope you're noticing that the standard deviation is getting smaller with each of these graphs as well. Notice this graph, see, the width of the graph is getting skinnier as the larger you get. So on the previous slide, we had a mean of 3.5 and we had a standard deviation of 1.708. So, as the central limit theorem tells me, the mean becomes normal as the sample size increases, regardless of the shape of the original population. And again, for some reason, that magic number is 30. It's like normality occurs once you hit to 30 in your sample or more. So if the original population is not normal, or if you don't know if it's normal or not, you should always start with 30 for your sample means. You want to take 30 in your samples, and therefore the normality should occur. The standard deviation in this one, we would take and divide that number by the square root of 4. Then we would divide this one, 1.708, by the square root of 10. That gave me this new standard deviation here. And in the last one, we took that standard deviation and divided by the square root of 30. And those standard deviations did get smaller as the sample size got larger. So suppose that the mean time for an oil change at a 10-minute oil lube is actually 11.4 minutes with a standard deviation of 3.2. You're going to take a random sample of 35 oil changes as selected, describe the sampling distribution of the sample mean. See, y'all, we're taking 35 in our sample, so it doesn't matter if my original population was normal or not, because we're talking about the sampling distribution of a sample mean. As long as it's 30 or more, normality will occur. So we will say that the sample means will be normally distributed. So this is saying sample mean is approximately normally distributed with the mean of, my mean remains the same, of 11.4, but the standard deviation is going to be shrunk. You're going to make it smaller by dividing by the square root of how many is in the sample size. So the 3.2 divided by the square root of the 35, that gives me my new standard deviation. So if a random sample of 35 oil changes is selected, what's the probability the mean oil change time is actually less than 11 minutes? So I want the probability that the mean, that's the x bar, is less than 11. Well, remember, I'm going to have to do this value minus the mean divided by the standard deviation. That would give me my z-score. Then I want to do a normal CDF from -100 to that z, because I want the probability that it's less than. So again, that would be, then I would run a normal CDF. Okay, that was under second distribution. The left bound would be -100. My upper bound would be this -0.7395, and that would give me my probability of selecting a random sample of 35 oil changes, and the average of that group of 35 being less than 11 minutes. I have a 22.98% chance of that occurring. If you look under your Chapter 8 formulas on your formula sheet, you will find these two formulas for the sample mean. So again, the distribution of a sample mean, if the original population is normal, then the sample size did not matter. It'll be normal no matter what. If my original population is not normal, or if you don't know if it's normal or not, you must have at least 30 in your sample for the distribution of the sample means to be normal. In both cases, the sample mean will be equal to the mean of the original population, but the standard deviation of the sample means would be the original standard deviation divided by the square root of how many is in your sample. Good luck to you on this assignment. Please do at least the multiples of 4 prior to coming back to class. Thank you.